All right, so let's see how you did with transforming this data and determining which is the best equation to use. All right, so number one, when you did x log of y, so remember this is list 1 and list 4, this is the equation you should have gotten. Remember, we're putting the log in front of y because we took the log of y. This was your equation. Let's take a look at our r squared and our r value. We had 0.84 and 0.91. Notice my graph is still kind of curved, and then take a look at my residual plot. It still shows a pattern. So this is going to basically all tell me that this is not going to transform this data in order to make it linear. Let's take a look at the next one. Now, the next one was list 3 and list 4. Now, remember when we wrote our equation, we put the log in front of y because we took the log of y, and we put the log in front of x because we took the log of x. Okay, and then we're going to take a look at the residual plot. All right, so number one, when I take a look at the graph, this looks a lot linear than the other ones did. It has a slight curve to it, but I could make a pretty good line through it. Let's take a look at my r and r squared. We have 0.94 and 0.97, which is better than 0.84 and 0.92. And my residual plot, I have equal amounts above and below my x-axis. So therefore, we're going to say that the best transformation here is going to be my second one, which is log of x, comma, log of y. Okay, and so like I said, just make sure when you write this that you're writing the log in front of y and the log in front of x, because we had to take the log in order to make it in a linear equation. Okay, and the reason was A, this has a linear pattern, the r and r squared were high, and the residuals were random. So those are three things that would tell us that that is the best equation. Now, the reverse transformation here, I'm going to show this to you. Now, please keep in mind that you can use your calculator to do this exact same thing. Honestly, I would not do this by hand. You can take a look at this. I'm not going to go through this, but if you want an explanation, just shoot me an email and I'm happy to. Now, just check on your calculator. You'll get the same answer. So please keep in mind, you did x comma y. You knew that the log of x and the log of y transformed your equation. So what that's going to tell you is that this was a power equation. So remember, you're going to go to stat, and then you're going to go to calc, and then you're going to go to power regression. But when you do that power regression, you're going to use list 1 and list 2, because we are doing the regression. We're getting the power equation from the original, and you should get something very similar to what you have here. Okay? All right, now there are two major equations. These are really the only two that you're going to see on your AP exam. So you have two transformations. Number one is going to be x log of y, or x natural log of y. They're both exactly the same, and it doesn't honestly matter. So I remember it as I had to do one transformation. Okay, one transformation means the original was exponential. The second one, when I took the log of x and the log of y, I'm like, that's more powerful. I had to take a transformation of x and y. Now, you can either do the log of x and log of y, or you can replace log with natural log of x. It's totally the exact same thing. Just make sure when you write your equation that you put the natural log in front of x or the natural log in front of y, if that's what you choose to use. Okay, all right, so let's take a look at this example. The following chart gives data on the mean income by age. So I would like you to try this one. Number one, construct the scatter plot, making this list 1 and this list 2. Describe what the plot tells you about the data. Is it curved? Is it linear? Is it nonlinear? Okay, and then you need to find and plot the least squares regression line on your scatter plot. Now, please keep in mind, remember this has to be the transformation. So you are going to have to find which list gives you the best transformation. Okay, so go ahead and take a minute and try that. And then once you've done that, you can pause this video and then you can come back and check your answer. Okay, so let's see what we did. All right, so number one, if you take a look, this original data. This is list 1 and this is list 2. All right, so if you notice here, when I graph this, actually a curve is going to fit a lot better than my line. So I know that I need to transform the data in order to get my equation. So if I were just to write the equation as is, I would get y hat equals negative 48.23 plus 2.691x. But the graph tells us that as age increases, so does the income, but the graph is curved, so really a linear equation is not best for this. It's either an exponential equation or a power regression. So we're going to figure out which one is best and which one's going to make it linear. So let's comment on the goodness of fit using the R squared, and residual plot. So this is still just for the original one. Now, notice how your R, basically that R value, remember, it does not tell you whether or not it's linear. So it tells us there is a strong positive correlation between age and income. Like, that's good. And then that also is going to tell us that 93% of the variation in income can be explained by the least squares regression line that relates the two. Now, notice if we check the residual plot, okay, that shows us that there is a definite pattern. So therefore the data is definitely not linear, which we could obviously see when we graphed it originally. Okay. Now, to get the residual plot, remember what you're going to do is you go to second stat list and then you go to residual and hit enter. If you need more instructions on that, just let me know and I'm happy to help. Okay, so now let's do the appropriate transformations and see what happens. Okay, so hopefully you already did this. And remember what you're doing is we're going to do x log of y. So this is list 1 versus list 4. This is going to be list 3 versus list 4. Okay, so let's first compare our values. So 0.999, 0.98. Oh, I'm going to kind of guess that exponential is going to be a little bit better. Notice when I graph x log of y, that's pretty linear. Notice when I graph log of x log of y, I still kind of have a curve here, which isn't fantastic. It's still curved and I have a lower R value. Let's now compare the residuals. The residuals for this one are randomly scattered above and below, okay, which is good. So now we know A, the R value is high, B, my graph is linear, and C, my residuals are randomly scattered above and below, therefore it's most likely the best fit. Okay, so since we had this is going to tell us that the original was exponential. So we want to calculate the least squares regression line for the best fit data, then find the reverse transformation. Now keep in mind, you can use your graphing calculator to find the reverse transformation. So when you did this on your graphing calculator and you did list 1 comma list 4 for your linear regression, you should have gotten the log of income hat equals your y-intercept was 0.8418 plus 0.0212 for age. Now remember, since this was x log of y, we have to put the log in front of the y to show that we took the log of it in order to make it linear. When you do the reverse transformation, you should have gotten your predicted income. Always just make sure that that has the hat on it and is defined, equals 9.647 times 1.05 to the x. Okay. Now you can do this on your graphing calculator. We knew this was exponential. So you can go to stat, you can go to calc, and then you can go to exponential regression. Okay, and that will get your equation. Just keep in mind, you're doing that on list 1 and list 2 because that was the original shape of your data. Okay, so if you would like to try this, you can. So Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit would double every 18 months. And for those of you who have taken computer science, you might know that this is Moore's law. Okay, so technology is doubling every 18 months. So here are data on the dates and number of transistors for Intel microprocessors. So here's the dates, and then here's the number of transistors. So every 18 months, basically, we're doubling. Okay, so hopefully that will show you that that is potentially an exponential model. All right, so the figure below shows the growth in the number of transistors on the computer chip from 1971 to 2010. Notice the years since 1970 were used as the explanatory variable because we don't want to write like 19. All right, so we were talking that potentially Moore's law should be an exponential model since it's doubling every 18 months. Let's just check and make sure that that is going to be the case. All right, so a scatter plot of the natural log of the number of transistors on a computer versus years since 1970 is shown. So basically we were taking, so notice here it's labeled the year since 1970 and we took the natural log of the transistors. Based on the graph, take a minute and explain why it would be reasonable to use an exponential model to describe the relationship between the year since 1970 and the transistors. Okay, now, if an exponential model describes the relationship between the two variables, then we would expect x natural log of y, or you could also use log of y here, same thing, to be roughly linear. Well, if we look at this actually has a pretty linear pattern until we get to this point right here. So I would say that an exponential model would seem reasonable in this case. Now, here's another example of Minitab. The Minitab output below is from a linear regression performed on the transformed data. So please keep in mind your transformed data, remember, was x natural log of y. And make sure when you write the equation, you define any variables that you use. So why don't you go ahead and take a second and try this, since this is something you will need to do on the AP exam. All right, now let's take a look at the answer. So number one, remember the top always represents your y. The bottom represents your x's. Now what I'm gonna do is I'm just gonna put natural log right here because that's gonna remind me that I took the natural log of y, but not x, okay? So this is going to be my y-intercept, and this is going to be my slope, okay? So when I write my equation, I need to write the natural log of my y values because I took the natural log here. So in this case, the natural log was the transistors. Okay, that's in context. Make sure you put your hat there. Here's my y-intercept, the 7.0647. Here's my slope, and then notice my x. I did not have to put the natural log in because that did not, I did not have to take the natural log of it for my transformation, and this is in context, year since 1970. All right, now we're going to use our model in part B to predict the number of transistors on a computer chip in 2020. All right, now remember this is year since 1970. So how many years is 2020 from 1970? Okay, well that was 50 years, okay? So we're going to plug in 50 here. Remember this side you can do directly on your graphing calculator, okay? Now what we have left is we have the natural log is equal to 25.3562. Now, this is not solved yet for transistors. I still have that natural log in front of it, okay? So I just rewrote natural log as log of E because log base E is the same thing as your natural log, okay? All right, that's going to help us solve to get that transistors alone. So then here's what I did. I rewrote this as an exponent. So if you take E to the 25.3562, which is what I did right here. So base of your log is the same as the base of your exponent, 25.362 equals your transistors. So then I can just type this on my graphing calculator and get my answer. Okay, so this model predicts that an Intel chip made in 2020 will have about 100 billion transistors. All right, and then if we just take a look at the residual plot for the regression in part B, okay, so if we take a look at the residual plot of this equation right here, this is going to show us that it's randomly scattered above and below the y-axis. So therefore, we are reasonably comfortable to make predictions using the linear regression model.